Question 5. In an amusement park, a passenger of mass 60 kilograms travels upside down in a carriage at the top of a circle of radius 6 meters at a speed of 12.3 meters per second. Draw a force diagram showing the forces acting on the passenger. So this is more complicated to do than it initially sounds. So I've got my loop. Its radius, it's going to show radius, is 6 meters. We've got someone who's going to come in and travel upside down at the top. I'm going to have them going that way at 12.3 meters per second. And they've got a mass of 60 kilograms. Now, as we saw in the last question, the size and the size of the contact force compared to the weight depends on the forces needed to make this thing go in a circle. Unlike a motorbike going round in a sphere, on a roller coaster, you can have straps that go over your shoulder. So you can have a contact force that pushes you down at this point. If you sort of feel like you'll be pushed into your seat, you'd certainly have a contact force that was downwards. If the roller coaster went very slowly over the top, you might feel like you were sort of hanging out of your seat and the straps were holding you in. So we could have a contact force that's upwards. So in order to answer this first part of the question, we need to have a sense of what the size of the weight is compared to the size of the centripetal force required to make the person go in a circle. So we need to do a couple of calculations. The weight is calculated as mg. So mg here is 60 times 9.81, which is 589 newtons. Now so that's acting down on the person. There's a weight force. Now we need to know how big the centripetal force needs to be on the person. So I'm going to label it FC. This is equal to mv squared over r. So 60.0 times 12.3 squared over 6. This has a value of 1,510 newtons. In other words, the weight alone was not enough. We need an additional force acting towards the center of the circle. So in order for circular motion, we need a resultant force of 1510 newtons towards center, which in this case, of course, is downwards because we're at the top of the loop, i.e., we need an additional, so the difference between these two, 1510 and 589, so that's 921. We need an additional 921 newtons of downward force. And that must come from the contact force. So we haven't answered part A yet, but I'm going to move into the part B box. Our free body force diagram should have the weight going down, and we know its size is 589 newtons. It should have an additional force going down. On a free body force diagram, we tend to show all forces coming from the center. I've put them together tip to tail here, just to get across the idea they both act down. This is an additional force of 921 newtons. And of course, this effectively answers part B of the question too. The answer to B is the direction, the size of the force is 921 newtons and the direction is downwards. So in this particular roller coaster, if we're imagining it, the person would feel like they're being pushed into their seat. If we wanted to measure the size of this, we'd say that because the contact force on them is nearly double their weight, the size of this force, the size of this acceleration, we'd say is a 2g acceleration when we come to look at it. So you'd feel fairly squashed into your seat as you went over the top of this loop.